sharing the screen. Okay, so good afternoon everyone. This is the fourth interactive session for the NPTEL course named Experimental Physics 1, which is being taught by Professor Amal Kumar Das from IIT Kharagpur, and I am Rinalini, PMRF Research Scholar from School of Physics, University of Hyderabad. I am a teaching assistant for this course. So this is the interaction session that happens every Saturday from 3 p.m. to 5 p.m. and you can find these interactive session recordings on the Google Drive link, as well as this PPT I always share after the session, so you can find these things there as well. Okay, starting with today's session. First we'll recap what we did last session. In last week we discussed these basic components that we find in a laboratory, which are resistors, capacitors, inductors, and various wires and connectors. We also understood the theory of these components, and we also derived the formula when these components are connected in series or when they are connected in parallel, and based on these conditions we also carried out many problems. So this is what we did last time. So last week we also discussed that whenever we are conducting an experiment in a lab, how we should collect the data, like we should take care of what all the things we should take care of, like repeating the measurement and taking the average of it, then how to take suitable x steps in x variable, and then note down corresponding y variable. Also we should be choosing appropriate instrument based on the least count we want for particular experiment. We also talked about different type of graphs and which is used in which condition and what is calibration. So these things we discussed under basic analysis. Now the next thing that we are going to discuss today is the error analysis. Whenever we carry out any experiment, there is some error analysis as well to be done. So we know that whenever we are carrying out any measurement, let me take my pen. Whenever we carry out any experiment or whenever we measure any value, there is some uncertainty. There is some uncertainty in that. I mean, like if we measure any, say, length, there is again say a rod of some length, and I am measuring it using a meter scale, then there will be some, and say I find out the length to be 23.5 centimeter. Then this value may include some uncertainty based on the least count of instrument that I have used. Least count of instrument, like in this case we have used meter scale, right? So meter scale has 0.1 centimeter least count. It cannot give me more precise value than this. So there could be error in this value. So in similar way, there are various other conditions I will discuss in detail later what or can be the causes of these kind of error. But what we know is that every time we carry out some measurement, there is some uncertainty, like this last digit. If you remember, in one lecture we had discussed that significant figures, right? We had discussed what are significant figures, significant digits. In that we also understood that there are some reliable digits, and then there is one uncertain digit. Including everything, we call it significant digits. So that is what uncertainty or approximation. Like sometimes we just tell that length of something, if we are saying approximately the length could be 2 meter, or something. So I mean, we are not 100% sure that the value is this. There is some uncertainty. We are not 100% sure means we are not certain. There may be some value may be little up or down than what we are saying. So that uncertainty or that approximation is always there. There are different reasons behind this that we will discuss soon. So first again, we recall earlier we had understood what is accuracy and precision, because whenever we carry out any measurement, there is the measurement, we need to find out how much accurate it is and how much precise it is. So recalling the definition of accuracy and precision again. So accuracy is measure of how close the measured value is to the true value of the quantity. Again, like for example, if I am carrying out some experiment to find out the value of acceleration due to gravity, we know that acceleration due to gravity of a free falling body is 9.8 meter per second square, right? This we know, it is acceleration due to gravity for any free falling body on earth. If I am carrying out any measurement and the value I measure is say 9.4 meter per second square, so this value, and say some other person, he or she also carried out some experiment and he found out it to be 9.11 meter per second square. That means my experiment is more accurate than this because it's closer to the true value, whereas this person's measured value is more precise because its resolution. So precision we define as up to what resolution or limit the quantity is measured. So this person's experiment is giving us up to second decimal digit. So his or her experiment is giving more precise measured value, whereas mine is more accurate. So I mean, this is what we understood with accuracy and precision. Okay, so as we talked about that any measured value has some error associated, and there are many sources of these errors. Like here, if we talk about in general, if we define error in any measurement can be classified as systematic errors or random errors. So what is systematic errors? Errors associated with each data throughout the measurement in the same way. These errors shift data in one direction, either positive direction or negative direction. What do we mean by this is, like when we call it systematic error, when the data is always shifted in one direction. For example, instrumental error, that is zero error. If we take example of zero error, if you remember, we had discussed about vernier caliper, screw gauge, right? And we had discussed that they have some zero error. For example, if I have a vernier caliper, if you remember, these are the jaws of vernier caliper. There is main scale, and there is, when this jaw is completely closed, right, when this jaw is completely closed, then we know that, I mean, there is this main scale and there is vernier scale. There are different divisions on both, but when this jaw is completely closed, then the zero of main scale should match with the zero of main scale should match with the zero of vernier scale. When they exactly match, then we say there is no zero error. No zero error. But if the vernier scale 0 is slightly on the right side, then we call it positive zero error, right? What does that mean is, every time whatever measurement we will take, it will be a little higher value. Whatever I am measuring, instead of getting the actual value, I will be getting some positive error in that value. It doesn't matter if I repeat it 2 times or 3 times, if that instrument has some error, some positive error, then every time whatever I will calculate, it will be a little higher. Say like some, because least count of vernier caliper is 0.01 centimeter. For example, I am measuring some length of something that comes out to be 2.52 centimeter, and if I am told that the zero error of there is positive zero error, and that is 0.01 centimeter. That means instead of the actual value is 2.51 centimeter, but since there is positive error of 0.01, so I am getting 0.01 extra here. Again, if I do measurement for some other object, say it is 32.63 centimeter, that means here this 0.01 centimeter again is the extra value I am getting because of the zero error. So what is happening, whatever I am measuring, every time I am getting a little higher value. So similarly, if there is negative zero error in any instrument, then I will get all my values little lower than the actual value. So these kind of errors are systematic errors, and this is also example of instrumental error. This is one kind of error. I mean, what we are noticing is that each data, when in this kind of error, each data is shifting either in positive direction or negative direction. So one is like the zero error. Another error could be calibration error. For example, say that we bought a thermometer which maybe its calibration is not correct. Last class we had also talked about calibration. So maybe that thermometer we bought is a cheap quality and its calibration is not correct. So instead of that thermometer, say that when we dip it into water and we are boiling this water, so instead of the boiling starts and we see that the boiling is shown at 103 degrees centigrade. See, we all know that boiling of water starts at 100 degrees centigrade, right? But I again change, I take another vessel of water, again I use this thermometer, and again I see that it's starting at 103 degrees centigrade. That means there is problem with this thermometer calibration. It should be calibrated at 100 degrees centigrade, but mistakenly it's calibrated at 103 degrees centigrade. So this is also one type of error. So this kind of various sources of errors are there. This is the case of systematic error. There could be random error also. In random error, it could be either in positive direction or negative direction. We cannot predict that, and these are these are different than systematic because they are random. There we cannot know the cause, and it's very random and unpredictable. For example, say I am carrying out an experiment to find out time period of a pendulum oscillation. I am oscillating it, and instead of freely moving, assume that I have a wind coming. Like I am doing this experiment in outside and there is strong wind flowing. Then what will happen? Of course, this motion, instead of it's moving on its own, it's getting external force from the wind blowing outside. So from this experiment I will not get correct value, right? And even if I repeat this experiment, since the wind is flowing maybe in random direction, after some time the wind is flowing from this direction or from this direction, a different direction. So every time I'll get some other value and I will not know if that error is positive or negative. So it's like random in this sense. These random errors could also be, what do we mean by personal error? This personal error means that, for example, this is depends on the person who is taking that measurement. For example, I am carrying out a measurement, and when I am reading, like even from the scale, when I am reading the value, if I am keeping my head on the right side and I am seeing, then maybe instead of seeing that object here, if I am seeing from extreme right, maybe I'll see the object is here or something. This happens. This is called parallax. Or if I am seeing from the left side, I may see that the object is here instead of seeing it here. So that could be one type of error, personal error. Another could be some very blunder kind of error, like say I carried out an experiment and instead of writing 23, maybe I measured it 20 and mistakenly I wrote 23 millimeter. Okay, then later I'll see and this is very small value, but maybe I made this mistake. So this could happen at the level of instrument is giving the correct value, but maybe mistakenly instead of writing centimeter I have written millimeter. So these kind of random errors are called personal errors. So okay, moving on to the next type of random error, it's called least count error. That this depends on the least count of the equipment. Like we know for vernier caliper the least count is 0.01 centimeter, right? If I want to get more precise value, I'll go to screw gauge, whose least count is 0.01 centimeter, right? For screw gauge the least count is 0.001 centimeter. So the more close I can go to the actual value, the less will be the least count. So last time also we had discussed that we should use appropriate equipment depending on what we want to measure. If we want to measure the distance between two buildings, we will not use screw gauge or vernier caliper, right? They will use some bigger measuring tape than the normal meter scale. Whereas if I want to measure the thickness of a page, there it will be better to use screw gauge or vernier caliper instead of using the 15 centimeter scale. So these are the different sources of errors that we can encounter whenever we are carrying out any kind of experiment in our labs. So I hope we understood what are the different sources of errors, and keeping these in mind, next thing is how do we understood what are the sources of these errors. Now we want to understand how do we express these errors. I mean, I told that whenever we carry out the experiment there is some error, like instead of like if I measured something to be 23.5 centimeter, there is some error in it, but how to tell someone what is the error in this measured value. So we define any measurement, the error in the measurement in three forms. One is called absolute error, another way is relative error, and there is one more way called percentage error. So what is absolute error? The magnitude of difference between the individual measurement and the true value of the quantity is called the absolute error of the measurement. So again, taking the example of acceleration due to gravity, we know that the accurate value is, okay, just taking it to first decimal digit, 9.8 meter per second square we know. And if I conduct one experiment in which I found the value to be 9.7 meter per second square, then I can tell that the error in, this is what I have conducted the experiment. So the error in this will be the difference between the individual measurement and the true value. So absolute error will be the value I measured minus the true value. This will be 9.7 minus 9.8, that is this will be minus 0.1 meter per second square. So this is the error. The error is negative because my value was smaller. If my value will be larger than the actual value, then this will be positive. So it also tells like if the value is large or small by showing this negative sign. So one way of expressing the error is absolute error. But we express absolute error always as magnitude. I mean, when we subtract this, we get the value plus or minus depending on this value, right? But we always express this as absolute. This symbol defines that what inside whatever will be the value, but outside we'll take it as positive. So absolute of this means 0.1. So absolute error we always express as positive. So this is one way of expressing the error. Another way of expressing the error is taking relative, it is called relative error. It is the ratio of mean absolute error to mean value of quantity measured. Okay, so another thing that I want to tell is, another thing that I want to tell is that, okay, for this experiment, like we already know that acceleration due to gravity is 9.8, but many times we don't know what exactly is the value, right? For if I am carrying out some experiments, say like earlier we had discussed, if there is a circuit and there is a resistor and this is a battery connected of voltage I, and there is a emitter, there is a voltmeter connected here, and I want to find out what is the current in this circuit or what is the voltage drop across this resistor or something. Here there is no ideal value of I, right? It depends on whatever resistance I am connecting here. So there is no true value in that sense. So how we find out the error here? So what we do is we carry out the experiment many times, and every time I'll get different value of I, right? First time I calculated, I get one value. Second time I'll get some almost same value, maybe exactly same, or maybe it will be something like depending again on what is the least count of this emitter. Say first time I got 3.36 ampere, next time I got 3.35 ampere, then third time I got 3.3, say 7 ampere. So what we can do, because here is we don't know what is the true value, unlike this case, this kind of experiment. So in usually generally what we take as true value is the mean. Whenever we are carrying out any experiment, we repeat it many times. This is also done to reduce the error as we had discussed earlier, and also when we take the average of these three values, whatever we will get, that we treat as true value. We call it the mean measured value. So this is I1, I2, I3, right? Then I average, or we can call it I average, or we can call it I mean. We can call anything, both are correct. Let me write like this. So this will be the average of these three values. For example, if I see, okay, we'll do in detail, we'll do these calculations, but I just want to tell you that for some experiments we know this true value and then we can calculate the error accordingly, but sometimes we don't know exactly what is the true value. That time we repeat the experiments, and average of all those experiments is the mean value, or we can say the true value of that particular parameter. Okay, so moving on to the relative error. What is relative error? It is the ratio of mean absolute error to the mean value of quantity measured. So how to define this is, here like I told, the error is what we measured minus the true value. So for in this case, the error in current, if we want to find out, that will be when I measured this I1, that I mean the error in first value will be this I average. Similarly, the error in I2 will be I2 minus this. This I average is same, right? We have taken average and the value will remain same. Similarly, we will calculate for the error in third measurement, which will be this I average. Now the error in first experiment, second experiment, third experiment, when we will take average of these three errors, we will get our mean absolute error. So mean absolute error will be delta I mean, it will be the average of all these three errors. We'll do this in one example next, so it will be clear. So this ratio divided by this I mean, this ratio is called the relative error. So this is another way of expressing. Third way of expressing the error is in percentage. When this relative error is multiplied by 100, we get it in form of percentage, right? So that is called percentage error. So these are the three forms, and let's understand it by using this example. So the example is, we measure the period of oscillation of a simple pendulum in successive measurements. The readings turn out to be there are 2.63, 2.56, 2.42, 2.71 and 2.80 seconds. So we repeated this experiment 5 times. Calculate the absolute error, relative error and percentage error for the time period. Okay, so this is again some pendulum we used, and by carrying out this measurement, we did it 5 times, and every time we found out the time period like this. In first time we found out to be 2.63 seconds, then second time it was 2.56 second, 2.42 second, fourth time it can be same also, but since it's random and error is not exactly in our control in these kind of cases, so we cannot know and predict what exactly these values could be. So I mean, this is just given that this is what we found out here. After repeating every time, we were finding these values, and we did it totally 5 times, and these are the values we obtained. Now we need to find out the absolute error. So to find out absolute error, we know first we need to, these are different time periods we have found out. We want to tell what is the value of time period of when from this experiment. For that we cannot tell that it was 2.63 one time and 2.56 another time, so we will tell the average of this. So we will tell the mean or the average of these time periods. So time period of these average will be, I'll do it in calculator. So average of 2.63 plus 2.56 plus 2.42 is 2.71 plus 2.80 divided by 5. Okay, so the value after using the calculator, the value I am getting after dividing it by 5, I am taking the sum of all this and dividing by 5, I am getting 2.624 seconds. Okay, but now keeping in mind what we had discussed about significant figures, right? When we are adding everything and dividing by 5, since the significant figures here are 3, right? In all these measurements, significant digit is 3. Then my final value also should have significant digit in 3. So I will round off this, and then I'll get 2.62 second, right? After rounding off, it will be 2.62 second. So this is the correct way of telling the average time period. This is the correct way of telling. Now this I found out the t mean, so that if somebody will ask what is the time period you found out from the experiment, then we can tell this is the mean value we found out from this experiment. Now to calculate absolute error, the absolute error in first experiment will be this t1 minus t mean, right? This we have understood. So that will be 2.63 minus 2.62 second. This will be 0.01 second. Similarly, absolute error for this will be 2.56 minus 2.56 minus 2.62. This will be 6. 0. Sorry, this will be negative, but again because absolute error is always positive, so we will take positive of this and it will be 0.06 second. Then the absolute error in third experiment, it will be 2.42 minus 2.62. Again taking the positive of this, it will be 0.2 seconds. For T4, 2.71 minus 2.62. Is it 9? 0.9 seconds. And T5, it will be 2.80 minus 2.62. It means it will be 0. 2.8 minus 2.62. 0.18 second. This is what I'm getting here. I should take care of this decimal digit also. This is fine. This I should correctly write like this because there are two decimal digits here. I should write like this. Oh, this is a mistake. 0.09 and this will be 0.8 seconds. So these are the absolute errors I have found out in this. Now I'll take the mean of these errors. So delta T mean will be average of these errors. This will be 0.01 plus 0.06 plus 0.09 plus 0.18 divided by 5. So the average I am getting after adding and dividing by 5, the value I am getting is 0.108 seconds. Again, what we need to keep in mind is these errors here were up to second decimal digit, right? So in my final result also should be up to second decimal digit. So I will round off, and after rounding off I'll get 0.11 second. So this will be the correct way of writing the mean absolute error. Now for relative error, we know there is no space, I'll write here. The relative error we know, is defined as delta T mean, the mean of all the errors divided by the mean of measured value. So this is 0.11 divided by, what was it, 2.62. When we'll do this, we'll find 0.11 divided by 2.62. Again, answer I am getting is 0.04. There are many digits here, something like this, but keeping significant figures, here is 3, here is 3, so I'll keep up to 3. So 0.042 is the relative error in this case. Now the percentage error will be what? Relative error multiplied by 100 gives the percentage error. So in this, when we multiply by 100, we will get 4.2%. So the percentage error will be 4.2%. So these are the three different ways of expressing errors whenever we conduct any experiment. These are the three different ways in which we can express the errors. This is valid for all kind of experiments. This is just one example. Now, okay, so I had more space. Now combination of error. This is also very important. what to do when we have to add one or two errors. For example, mm, there is a quantity that, for example, like we know, right, when in any in Ohm's law V depends on IR like this. So what if there is some error in current and there is some error in resistance value, whatever we measure, then how should we express the, if there is some error in I and there is some error in R, that means whatever we will calculate voltage, that will also include some error. But how should we, what should be the maths we should follow for that final error in the value of voltage? That is what we are going to understand here. So one thing is error of a sum or a difference. For example, there is some parameter which is the sum of these two parameters A and B, and say when we measure A comes with some, A is expressed like this. Why? Because when we measure A, it's giving some value and some error. Similarly, when we measure B parameter, it could be anything, here we are just taking in general. So when we take this B, so what we find out is this also has some error, and we can express this like this, and that means this final thing will also have some error. Okay, we'll see that later. So yeah, we can write like this, this will also have some error. So the error in this Z quantity will be putting this, sorry, A plus delta plus minus. Actually the error could be expressed as plus minus 1 because it could be positive or negative. So we express it like this. This is one thing, and plus B plus minus delta B. Now this will be A plus B plus delta A plus delta B. So we can clearly see that this is Z and delta Z is this. Actually there is minus sign also, I agree, but what this means is the maximum error can be delta A plus delta B. The minimum value of error could be delta A minus delta B. So whenever we calculate the final error, we always take the maximum value possible. So that's why when we add or subtract any two quantities like this, the error is always gets added. That is the rule. When two quantities are added or subtracted, absolute error in the final result is the sum of absolute errors in the individual. So it's always the sum. Let's do an example to understand this. For example, the temperature of two bodies measured by a thermometer are, okay, let's write here. So we are measuring temperature of two different bodies using a thermometer. Temperature of first body is 20 degrees centigrade plus minus 0.5 degrees centigrade. So again, to make it clear, what do we mean by plus minus is that the maximum, there is some error associated, okay, depending on maybe least count or due to any reason, there is some error. What we mean when we write plus minus is that I am telling that it's 20 degrees centigrade plus minus 0.5 degree, means the value is, the minimum it could reach is 20 degree minus 0.5, that is 19.5 degrees centigrade, and the maximum the value could be is 20.5 degrees centigrade. So whenever we tell like this, that means the value is in this range. 20 minus 0.5, that is 19.5, and 20 plus 0.5 degrees centigrade, that is 20.5 degrees centigrade. So the actual value lies anywhere in between. It could be 19.6, 19.7, 19.8 or anything. So this is the meaning of writing plus minus like this. Okay. So moving on to solving this question. The temperature of another body is given to be 50 degrees centigrade plus minus 0.5 degrees centigrade. And we have been asked to calculate the temperature difference and the error. So temperature difference means, what is the temperature difference between these two? T2 is 50 degrees centigrade plus minus 0.5 degrees centigrade. Okay, we have to subtract the value of T1, which is 20 degrees centigrade plus minus 0.5 degree centigrade. Now 50 minus 20, that means 30 degrees centigrade, and then we know the error is always sum. The error are always added. That means 0.5 and 0.5, it will be 1 degree centigrade, right? So the final value, the temperature difference can be expressed like this. The error in this temperature difference is plus minus 1 degree centigrade. So this is the temperature difference and the error will be this. Now when another thing is, next thing in combination of error is, we need to understand is error of a product or a quotient. Like when there is some quantity and it depends on A parameter and B parameter, it is as product of these two. Then if there is some error in this and this as well, then what will be the error in this Z parameter? So again, if we express as absolute this error, then okay, so the rule is when two quantities are multiplied or divided, relative error in the result is the sum of relative error in the multiplier. Okay, so if Z be what would be the error in Z parameter? That depends on this. A will be delta A times B plus minus delta B, right? Now when we will open the bracket, we will get A times B plus A times delta B. Then we will multiply here, that is plus minus delta A times B, and this plus this will be delta A times delta B. Okay, so what we can do is this delta A delta B we can ignore. Why we can ignore? So delta A delta B, we know these are errors. Errors are very small, like 0.1 or 0.01 kind of, right? Errors are very small, and we know if we are multiplying very small quantities like 0.01 times 0.02, then what will be the product? It will be 0.0002, right? That means when we multiply a value which is very smaller than 1, then the product is much more smaller. Keeping this in mind, we understand that this will be a very small quantity, so we can ignore this. Now we know that Z is AB, right? So substituting that, we will get AB plus minus, this will be plus minus delta Z. So will be again everything same, and I am dividing everything with AB. Say like I am substituting this AB and I am dividing this whole equation both side by AB. Then I will get 1 plus minus delta Z. This will be 1, and when I will divide this by AB, what will happen? A will get cancelled. I will get delta B by B plus minus. Again here, when I will say here, if I will divide by AB, So B will get cancelled, right? Only delta A divided by A will remain. So that is what delta A by A. I'm dividing both sides by AB, right? And this anyway we have ignored. So this one, both side we have 1, that means they can also get be cancelled. And what we get is delta Z divided by AB. AB is what? It's Z. So I can write like this. And this will be delta B divided by B plus minus delta A divided by A. Actually, this should be this plus is plus and minus again, or even okay, even if we consider this, the thing is, okay, so we understood what is relative error. Relative error is the absolute error divided by the measured value, right? So the maximum, so this is what we are getting here, and the maximum relative error would be delta B by B plus delta A by A, right? And the rule is that relative error in the result, that is the final result, the relative error is sum of relative error in the multipliers. So the errors are always again added, as we had seen in the case of sum or difference. Okay, so let's do a question based on this. So for a given circuit, this is the we conducted an experiment. We had an electrical circuit and we found out the value of voltage to be this and current is this. Find the percentage error in resistance. So we know from Ohm's law, V is IR. This means R is V divided by I. So the percentage error in R, right? So first we need to find out the value of R. Value of R will be, should we just, okay, percentage will be V by, okay, let me do this. So delta V by V, the percentage error in voltage will be this, right? This is the formula for percentage error. This, to write it in short, I'll write it like this. I'll denote it with this small delta V. This means the percentage error. The same way, the percentage error in current I'll define with delta I. That also means delta I by I into 100. Because we have been asked to find the percentage error in R. So I'm using this. So the percentage error in voltage will be, what is this delta V? Delta V is the error minus the, wait, oh, this is the error. It's already error. So it will be the error divided by the actual value into 100. So the percentage error is 5%. In voltage, the percentage error in current will be 0.2 divided by 10 times 100. So this will be 2%. So when we are finding out the, okay, now percentage error in resistance will be the percentage error in volume and percentage error in current. So we know it's always the, whenever we are multiplying or dividing such quantities, the errors always get added. That means whatever is the error in voltage, 5%, we'll add it to the error in current, that is 2%. So the total percentage error in resistance will be 7%. Okay. Okay, so this is another thing. Error in case of a measured quantity raised to a power. The relative error in a physical quantity raised to the power k is k times the relative error in the individual quantity. So what does this mean is that if there is a quantity where the raised to power if relative error of anything, say any parameter, is k times the relative error in individual quantity is raised to the power of I mean if the dependence something like if it depends on say b, if it depends on like this, then it will become no actually sorry if a quantity, say this quantity a depends on another quantity b, like this, that a is b to the power some constant k, in that case the relative error in a will be k times the relative error in b. Sorry, this is the correct way of what this rule is saying, that if a depends on b in this kind of relation, then the relative error in a will be k times relative error in b. And in general we can express this like this, that if there is a quantity which depends on a parameter, b parameter and c parameter in this particular way, okay, then the relative error in z will be depending on the relative error in this way. So how we get this is a to the power p, I mean the relation, I'm just expressing it in a different fashion, b to the power q, and since it's in division it will become c to the power minus r, right? And from what we had seen here, if it depends like this, then relative error is this power becomes it becomes the multiplication thing. So here also the relative error will be relative error in, where did my pen go? Yeah, so relative error in z will be p times relative error in a plus, because it's always going to add, the error always gets added, so it will be plus, then q delta b by b plus r. So you may think that it is a negative, but we know that error again will get added, so it will be like this. So it doesn't matter it is in multiplication or division, the errors are always added. So let's do a question based on this to understand. Okay, we have some questions based on these error analysis. The first question is from Joule's law of heating. So we know that Joule's heating is given by this formula, where R is resistance, I is current and T is the time. The current is measured as 5 ampere with emitter of least count 0.2 ampere. So what will be the value of current here will be, this is 5 plus minus, the least count is the error here, because it restricts, we cannot exactly tell what is the value, because of the least count of the instrument, the value could be, I'm measuring it 5 ampere, but because of least count error or least count limit, the value could be 4.7 ampere, no sorry 4.8 ampere, right? Could be between, what this means is the actual value could be between 4 ampere or between more than equal to 4.8 ampere, less than equal to 5.2 ampere. So yeah, this is what it means. So the current is 5 plus minus 0.2 ampere. Now the resistance is 100 ohm and it's given. We did not take the measurement of the resistance. It's just we have been given a resistor and we have been told that its resistance is R. We are not measuring. That means R is 100 ohm and there is no error is 0. Okay, there is no error. We have just been given that the value is 100 ohm. And the time is measured by stopwatch of least count 0.3 second and the time recorded is 2 minutes. That means the time is 2 minutes, and the least count of the stopwatch is 0.3 second. So the error is like this is second, okay, this is not 5, this is second. Since this should be in same SI unit, so it should be actually 120 plus minus 1 minute is 60 seconds, so 2 minute means 120 seconds, okay. So 120 plus minus 0.3 seconds. So this is how the time period can be expressed along with its error. Determine the percentage error in measurement of heat. So as I told, percentage error, that is in heat, sorry, 100. So instead of writing this, I want to write it like this. I want to denote it that the small delta H is the percentage error. So we know, and given in the question also, that this is the formula of dependence of heat on these parameters. That means the percentage error in H will be, we know this power will become multiplication, right? And when we want to find out the percentage error or relative error, this will be 2 times the percentage error in I, and since it is raised to the power 1, so it will be same. This is also raised to the power 1, this will also same, 2 times delta I. So before I calculate the relative error in I want to see that here it is getting multiplied by error in R, but we know that there is no error in R because we have not measured it and we have just been given the value, which is 0. That means delta R will be 0 and then multiplied by delta T. So that means the whole product will be 0, right? So that means, okay, I made a mistake here, I'm very sorry. We know that errors are always added, sorry, I'm very sorry about this. Okay, so the formula dependence is like this, but here we are calculating the error. So actually the correct thing is 2 times delta I plus relative error in resistance plus relative error in time. Errors are always added, please keep in mind. Yeah. So 2 times delta I, relative error in current will be the error 0.2 divided by 5 into 100. Now the relative error in resistance is 0, that is fine. Then relative error in time. Relative error in time is 0.3 divided by 120 times 100. This will be, if we'll calculate, let me see what it is. So this is 0.2 divided by 5 is 2. This will be 8 plus 0 plus this will be 0.25. So the relative error in heat will be 8.25%. So the correct answer is A, 8.25%. Yeah. Okay, so next question is this. A physical quantity X is expressed as this. Like this physical quantity X depends on these parameters A, B, C. K is a constant, but A, B, C parameter, it depends in this particular way, in this particular fashion. So and we have been given the percentage error in A, B and C are 1%, 2% and 4% respectively. Find the error in measurement of X. It's written error, but here all the options are in percentage. That means we need to find out the percentage error. So the dependence of X is K is a constant, so no error in this. and other things are a b to the power 3 divided by square root of c, and percentage error in a is 1%, error in b is 2%, and percentage error in c is 4%. So what is the percentage error in x? This is x. Okay, so k is a constant, so it doesn't contribute to the error. So relative error in x will be relative error in a plus relative error in b, and since it has power 3, so it will become 3 times relative error in b plus, if I define it again just to make it clear, it will be a b to the power 3, and this is root c, that means c to the power half, right? But this is in denominator, so when I'll bring it to numerator, it will mean like this, just to simplify. Okay, so what this anyway doesn't contribute, so we have removed it, and this is relative error in a plus 3 times relative error in b, and since it will be added, so half times relative error in c. Even though it's negative, we always find out the maximum error, so we consider the plus half and the relative error in c. So relative error in a is given 1%, relative 3 times relative error in b is given 2%, half times relative error in c is 4%. So this will be 1 plus 6 plus 2, 9%. So relative error in this quantity x is 9%. Okay. So the next is carrying out. Okay. So these were the combination errors we understood and did problem based on this to understand. Now we'll start with talking about experiments. So since in this course actually we will be learning how to do specific experiments, but all these 4 weeks we were understanding how to carry out experiment, how to measure, take quantities, what is the least count of any device, how to understand the error, because whenever we will carry out any measurement there will be some error corresponding to that value, right? So whenever in general we are carrying out any experiment, we need to understand the theory of that experiment. Before carrying out that experiment, we should understand what is the principle of that experiment, what is the theory of that experiment, so that we can carry out it correct way, and we know that what is the value we want to find out from that experiment, what is the aim of that experiment. So we should have the knowledge of theory of that experiment, and while performing the experiment, what all the precautions we should take, and then how to measure the value, and then how to report the value, right? Like we understood, whenever we are measuring any value, how should we express it along with its error. So the same way, when we will carry out these specific experiments that we will learn in coming weeks, so we should understand how to report those values and how to analyze those values. So this is the general thing whenever we carry out an experiment, and from this week we have started with this experiment called determination of Young's modulus of a material. So as we just talked that before carrying out any experiment we should know about such theory. So in today's session, first we will start by understanding the theory required for this particular experiment. So for determination of Young's modulus of a material, first we need to understand what do we mean by elasticity of a material. Your voice is also going. Okay. So elasticity, what do we mean by elasticity? It is the ability of an object or material to resume its normal shape after being stretched, compressed, twisted or pushed when the force is removed. So like this is the picture of a spring, right? So we know if we put force on both ends of the spring and we stretch the spring, till the time we are keeping its, we are applying the force, that means till the time I'm pulling the two ends, it will, the length will increase, but as soon as I'll release the force, it will come back to its original position. So such materials which can regain their original shape after that force is removed, they are called elastic materials. And this deformation, like whatever the change is happening in the material, these deformations are temporary, then that material is called elastic. On the opposite end, there are materials which are called plastic, because in for those materials, when the force is removed also, the deformation is permanent. For example, like if we understand, this is the spring, which when I stretch, it will deform, the length will increase, right? But when I will leave it, it will again come back. The same way, like this is a rubber band, as you can see, we are stretching it at the two ends, and it's getting stretched, like its length is increasing. But when I'll release that, it will come back to its original size. But sometimes also it happens that if we put too much force, right, if I'm pulling it too hard, that means I'm putting too much pressure or too much force on the rubber, then they will completely break apart, and then it cannot go back to its original position. So that also happens. For that also is true for every material, but that we'll discuss later. That is elastic limit. Any material has its elastic limit till which it can come back to its original position, but after that elastic limit, it cannot come back to its original form, and is completely deformed. So okay, so this we understood about elastic and plastic in general, and now we will understand what do we mean by stress and strain. I'm sorry, this should be strain actually. Let me correct it quickly. This should be strain on just a minute. Just to see the process running right. Okay, so to understand further, we need to understand what do we mean by stress and strain on a material. So stress is defined as the force per unit area within material that arises from externally applied forces. Means whenever we apply a force, like in this example we saw, right, we had spring, and if I'm pulling it from both ends, I'm applying some force, and that force when is expressed as force per unit area, that is called the stress of this material. When I'm applying this force, then the force per unit area acting on this material is defined as the stress in this material. Now when we apply this force and the stress is caused in this material, then it results in some change in length, right? If the original length was this, let's call it L, then if I am pulling it, then maybe this was the original length, and when I am pulling it, it increases a little bit more. This extra, this is some extra length. We call it delta L. This is the change in length. I mean, initially it was L, then finally it becomes some L prime. So L prime, this final length minus initial length is this change in length. So this change in length, the ratio of change in length divided by its original length, that is called strain in the material. So strain is the amount of deformation. Okay, so in this particular example, the deformation I am talking about is the change in length. For this example, The deformation is change in the length of the spring, but in general it could be any kind of deformation. So strain is the amount of deformation experienced by the body or that material in the direction of force applied divided by initial size or dimension of the body. Like in this example, the strain will be the ratio of the change in length divided by the original length. So same way it could be other dimension also, and the deformation is in the direction of the force applied. I had applied force in this direction, the change is in the same direction. So this is what is we mean by stress, and this is what we mean by strain. Now there is a law which tells us that whenever we apply a force on a material, then the stress in that material is proportional to the strain. This is a law given by a scientist named Hooke. That's why it's called Hooke's law. And this Hooke's law states that strain of the material is proportional to the applied stress and within the elastic limit. Again, as I had mentioned earlier, there is a limit up to which this happens. If I'm for example, if I'm stretching a rubber band too much, then eventually if it exceeds the elastic limit, it will completely break and it will not go back to its original size. So within elastic limit, the strain of material is proportional to the applied stress. This is Hooke's law. And we know, this, when we will take the ratio of these two, this is defined as elastic modulus. Ratio of stress applied to the strain produced in material is what we know as elastic modulus of the material. So, this is true for any object, and the ratio is what we define as elastic modulus. Now we will see that we have different kind of elastic modulus depending on different way in which the force is applied and different way the deformation is happening in that particular body or in that particular material. Okay, so first is Young's modulus. So the one kind of elastic modulus is Young's modulus, which is defined as the ratio of tensile stress divided by tensile strain. So what is tensile stress? So okay, let's first understand that again, instead of this time taking spring, I'll just take that, okay, I have a cylinder or some kind of wire. Wire is also a form of cylinder, right? Says I have some kind of cylinder and I am pulling it from both ends. Okay, I'm applying force in both direction. Then initial length was L and I'm applying force, I'm pulling from both ends, then it will become like this. Oh, sorry. So the length will increase till the time I am still keeping the force. Okay, then maybe the final length is L prime and this is delta L. Okay, as soon as I leave the force, it will come back to its original position, but till the time I am keeping the force, the length is this much. So in this kind of situation, we define this force as, force per unit area was stress, right? So this kind of stress we call as tensile stress. So tensile stress means stress that produces change in the length of material. This kind of force per unit area, that is stress, when applied in an object, okay, it causes change in the length of material. Then it is called, this type of stress is called the tensile stress. And what is tensile strain? The change that is happening in the length to the ratio of original length. This kind of strain is called tensile strain, and the ratio of tensile stress to tensile strain is elastic modulus basically, but it's specifically called Young's modulus. So this is what do we mean by Young's modulus. There is another kind of elastic modulus that is called bulk modulus. So in last case we saw that we applied direction and applied force in particular direction and it caused the change in length. Suppose we have a material, bulk material, where this time instead of applying force in one particular direction, I mean opposite two directions, we are applying this time force in all the directions and same force, not unequal or anything. We are applying force from all the directions and the same magnitude. That means if the initial volume was V, then till the time I'm applying the force, maybe it will, because I'm applying I'm pushing it from all directions, that means the force, the volume will become V prime. Till the time the force is still there, it will become V prime. That means there will be some reduction in its volume. So this kind of force per unit area is called volume stress, because it produces change in the volume of the material, and the change in volume to the ratio of original volume is defined as volume strain. So the stress, because it causes the change in volume, is called volume stress, and the strain, because it's associated with the change in volume, it is called volume strain. And because strain is the change divided by original dimension, it is this, and the ratio of volume stress to volume strain is called bulk modulus. Okay, so now let's do some questions based on this, our understanding of stress, strain and elasticity, plasticity, and this modulus, elastic modulus. We'll do some problems based on these things. So the first question is, okay, let me explain this something here. We'll need this formula also. Actually, this I have just defined that Young modulus is the tensile stress and tensile strain. Now we know, I expressed here that stress is force per unit area and strain is the change divided by original, right? So how we'll define Young modulus is, so that means tensile stress will be force per unit area and tensile strain will be the change in length divided by length. That means the Young modulus, which we denote by capital Y, so the Young modulus will be the ratio of tensile stress divided by tensile strain, right? That means this F by A, which is tensile stress, divided by tensile strain, which is delta L by L. If I simplify this, it will be F by A and delta L by L, right? So this is the formula we'll use to solve further problems. Okay. Similar way for this also it is true. Okay, so we'll use those things here. Two wires A and B are of same length and area of cross section, and they are stretched by same force. So we have two wires, wire A and wire B. They have same length. Okay, this is wire A, this is wire B. Their length is same, so I'll call both of them L, and area of cross section is also same. Means let's call it, this is wire A, this is wire B. Length is L, area is same, so I'm calling it A. Both I'm calling A because they are same, and they are stretched by same force, so I'm applying a force on them to stretch them, and the force is also same, so I'll call that force F. For both the wires, the force is same. The Young modulus of the material of A and B are, now they are different material, their young modulus, which is a constant value for any material, that will be they are different. Actually this, I'm sorry, is not the correct thing. This is actually this 1.8 times 10 to the power 11 Newton per meter square. I'm sorry, the exponents have come out here. It's actually this. This is also is. Anyway, I'll write here. Young modulus for wire A is 1.8 times 10 to the power 11 Newton per meter square, and young modulus for another material, another wire, because it's different material, the value is 2.4 times 10 to the power 11 Newton per meter square. This is the correct way. This is 10 to the power 11. Okay, 10 to the power 11 Newton per meter square respectively. The ratio of elongation of A is to B. That means we need to find out the elongation. Elongation means what is the, we are stretching means the final length is increased, but what is that change we want to find out for this material and for this material, I mean this wire, what is the change. So from the formula we just now did, we know that Y is stress divided by strain, and after simplifying this formula we got this, right? Using this, so y1 will be f1, so L1 divided by A1 delta L1, and y2 will be f2 L2 divided by A2 delta L2. But we know that for both the material the length is same, okay, the original length is same, and the area of cross section is also same, and the force that I have applied, that is also same. That means the force I have applied on both the wire, they are same, so I can call it F. Their original length is same, which is L. Their area of cross section, same length and area of cross section. So area of cross section is also same, that I can denote by A. Putting these values here, I will get y1 is equal to F L divided by A and delta L1. For y2 it will be F L divided by A delta L2. Now I have been asked to calculate the ratio of elongation of A wire to the B wire. That means what I have been asked to calculate is finally delta L1 divided by delta L2 is what I need to find out. So I'll take the ratio of y1 is to y2, or I can express delta L1. Okay, let's express delta L1 here in terms of these. Delta L1 will become FL divided by A times y1, and delta L2 will become F times L divided by A times y2. So delta L1, ratio of delta L1 and delta L2 will be FL divided by A y1, okay, divided by FL divided by A y2. So this will be cancelled, this will also be cancelled, this also cancel. What is remaining is 1 over y1 divided by 1 over y2. This means y2 divided by y1, and we know value of y2 is 2.4 times 10 to the power 11 divided by 1.8 times 10 to the power 11. Okay, so if we, this decimal point will go, if I divide it by 6, it will be 4 times, this will be 3 times, and this also will get divided. So what I will get is 4 by 3. That means the correct answer is this. The ratio of elongation of wire A to wire B is 4:3 is our correct answer. Okay. Now next question is this. Young's modulus of a perfectly rigid body. Young's modulus of a perfectly rigid body is what? So what we have been asked here is a perfectly rigid body. So what is a rigid body? A rigid body is a material or a body which which is that much rigid as something which is difficult to deform. Like a rubber is not rigid because we can easily deform it, right? Whereas if we have a stone, for example, then we cannot deform it with using our the usual force. The force by which easily I can deform a rubber band or a small spring, with that same force I cannot, even a little higher force, I cannot deform something like a stone or a brick. So those kind of bodies are very rigid. It's very difficult to deform them. So if in understanding keeping this thing in mind, uh, we have been given a perfectly rigid body, means it's impossible to deform that body. Then Young's modulus. We know that Young's modulus is defined as stress per unit area, stress, which is force per unit area, divided by the change in length to original length. Now when I am saying that for a perfectly rigid body, doesn't matter whatever force I am applying, there will not be any change because it's a perfectly rigid body. So the change in length will be 0. There will not be any change. That means whatever force I am applying, whatever is the area of the material, but the change in length will be 0. That means the Young modulus value will be infinite. So the Young modulus for this kind of material will be infinite. Okay. Now the next question is the ratio of the lengths of two wires A and B of same material. If they are same material, then their Young modulus will be same. Okay, again let's take wire A, wire B. So they are made up of same material, but I have made two wires, maybe of different length and different area of cross section. So wire A and B are of same material. That means their Young modulus is same, and I'm calling it Y because it's same. Ratio of length is 1:4. That means if we take length of wire A, we call it L1, length of wire B, I'm calling it L2, then we have been given that the ratio of length of wire A to wire B is 1:4, and the ratio of their diameter is 1/2. Diameter of wire A I am calling D1, diameter of wire B I am calling it D2. Then in the problem it has been told that ratio of their diameter is 1/2. They are stretched by same force. So I am applying same force on both the wires. Then the ratio of increase in length will be, again we have been asked to ratio of increase in length. Increase in length means delta L, and the ratio means we have been asked to calculate delta L1 by delta L2. So again, what is the formula of Young modulus? Force per unit area, and yeah, this is the formula. Now it's the Young modulus for both the materials is same, right? That means y1 is equal to y2. That means F1 L1 divided by A1 and delta L1 is equal to F2 L2 divided by A2 delta L2. They will be same. Now force that I am applying on both wire is same and I am calling it F. F1, F2 both are same, so I can cancel it out. Okay, and okay, let me write it like this. So I want to calculate delta L1 by delta L2, right? So if we rearrange this, we'll get delta L1 by, or okay, I'm cross multiplying, delta L2 by delta L1 will be A1 L2. A2 delta L2. What did I do? Delta L2 here, A1 here, A1 L2, delta L1, A2 and L1. This is just I am reorganizing the same equation. So because ultimately I want to find out this ratio. What I want to find out is delta L1 divided by delta L2. So taking reciprocal will be delta L1 by delta L2, which will be A2 L1 divided by A1 L2. Oh, so here I have actually taken capital small. Don't get confused. This is all, let's make it small. L1 L2. Here also let me do L1 L2. So the ratio of okay, so we know that area is pi r square, right? In terms of diameter it will be pi, radius is d by 2. So putting this thing here, A2 means pi d2 square by 4, right? By 4, and L1 divided by, for area 1 it will be pi d1 square by 4 and L2. So this pi cancel, 1 by 4 cancel. What we will get is d2 by d1 square, d2 by d1 square, and L1 by L2. d2 by d1, we have been given d1 by d2 is 1 by 2. That means d2 by d1 is 2 and square of it. L1 by L2, we have been given L1 by L2 ratio is 1 by 4. Oh, so this means 4 times 1 by 4. That means this is 1 is to 1. So the correct answer here will be 1 is to 1. Okay, moving on to another question. We have a wire of length 1 meter is made from 20 centimeter cube of copper. A wire of length 1 meter is made from 20 centimeter of cube of copper. Force F is applied on it such that its length increases by 4 millimeter. Another wire of length 2 meter is made from the same volume of copper. If the same force is applied, its length will increase by 1. Okay, so we have, let's call it wire A. Okay, the first wire I am calling it wire A. Its length is 1 meter. It is made of from 20 centimeter cube of volume. Okay, so volume is 20 centimeter cube. Force F is applied on it. So force F is applied so that its length increases by 4 millimeter. That means the change is 4 millimeter. Another wire, let's call it wire B. Another wire of length, original length is 2 meter, made from same volume of copper. Okay, so it's made up of same volume of copper. Both are made of copper. What do we understand from this? That Young modulus of both is same. I mean, because both are copper, that means same material, that means their Young modulus will be same. If the same force is applied, again the same force is being applied on this wire also, its length will increase by what? And I want to find out, here the change in length was 4 mm, and I need to find out what is the change in length here. Okay, now since the Young modulus is same, and again we know Y is defined as force unit area L by delta L, right? So for Y1 and Y2 they are same, that means, I mean what I want to write is like this, F1 L1 by A1 delta L1, because Y1 is equal to Y2, and putting the formula F2 L2 divided by A2 delta L2, and since same force is applied, that means this is same, so this will get cancelled, and L1 is what? L1 is 1 meter. Okay, so because the change in millimeter and the length is in meter, so I will convert this also in millimeter, so that the calculation is correct, because final answer also we want in millimeter. So 1 meter is actually 1000 millimeter, right? This will be 2000 millimeter. Okay, so keeping this things, or maybe we can do it later, let's keep in mind. Anyway, what we want to find out is delta L2, right? From this equation, let's rearrange this first. What I want to find out is this, delta L2. Delta L2 will be L2 times A1 times delta L1 divided by A2, and this will come in the denominator, that means L1. Now what is the ratio of area? So what do we know is volume of both these wires is same, but their length is different. We know that wire is like a cylinder, I'm sorry, first item is not good. So wire is like a cylinder of the height is some L, and this is area of cross section, right? So wire is basically a cylinder which is very long and very small diameter. So for both the wires the volume is same. So for first wire the volume will be, what is the formula? It's area of cross section times this length. Volume 2 will be A2 L2. So A1 by A2 is L2 by L1. Now L2 by L1, this L2, oh, I should have written like this. L2 is 2000 millimeter, L1 is 1000 millimeter. So 2000 divided by 1000. That means A1 by A2 is 2:1. Keeping this value here, A1 by A2, I'll write 2 by 1. Okay. And then L2 is what? L2 is again 2000. Delta L1 is 4 millimeter and L1 is 1000. So this will be 2 times 2 times 4. So the change will be 16 millimeter. So the correct answer will be 16 millimeter. Okay, we have one more question here. The question is the bulk modulus of a gas. The bulk modulus of a gas is 5 times 10 to the power 3 Newton per meter square. The additional pressure needed to reduce the volume of the gas by 1% is. So this is the question on bulk modulus. Till now we were doing question based on Young's modulus. Young's modulus means there was change in the length of the material. Now bulk modulus means there is change in the volume of the material. So we have been, so this bulk modulus we can denote using capital V. Bulk modulus is the, what is the formula? Volume stress divided by volume strain. The question is, we have been given the value of bulk modulus. Bulk modulus we have been given additional pressure needed. Okay, so volume stress means force per unit area, right? Volume strain means the change in volume divided by original volume. Additional pressure, we know force per unit area is also called pressure, right? So this we need to find out in this question, the pressure needed to reduce the volume of the gas by 1%. So force per unit area is the pressure that we need to find out, and we have been given that reduce the volume of the gas by 1%. That means we have been given this, the relative it's not error, I mean the relative change in the volume of this material. We want that how much pressure should we apply that the volume should reduce by 1%. It's some gas actually, yeah. So that volume of that gas should decrease by 1%. That means we need to calculate delta V, the change divided by original volume into 100. This is what we have been given, which is 1%, right? That means delta V by V is, actually this is this, delta V by V is 1 divided by 100. That means 0.01. Yeah, delta V by V is 0.01. After substituting, this is the volume of V. Okay, again from this formula, the formula finally becomes this, right? Delta V by V. Again rearranging, I will get delta V by V as P over B. Okay, but what we need to find out is this P. So this P will be delta V by V times B. Delta V by V is 0.01 and B is 5 times 10 to the power 3 Newton per meter square. It means the answer is 0.05 times 10 to the power 3, which means 50, and the unit of course we need to keep Newton per meter square. So the correct answer is this, which is 50 Newton per meter square. Yeah. So okay, so these were the questions related with bulk modulus and Young modulus. So what we did today is, first we understood how to do error analysis for any measured value, right? We tried to understand, okay. Quick recap. So we saw how to do error analysis when we do adding or when we do multiplication or division. We did questions based on this. Then in this week's lecture, actually the professor started teaching the specific experiments. The first experiment is determination of Young's modulus of a material, and when we want to do any experiment, we should have understanding of the theory behind that experiment. So in this class, in this interactive session, we discussed this theory where we understood what do we mean by elasticity, plasticity, what do we mean by stress and strain in a material, and what are the different kind of elastic modulus like Young's modulus, bulk modulus, and based on these we carried out these problems. So till now we have understood this. Now in this week's, the coming week's lecture, the professor will be teaching how to carry out this particular experiment and how to measure the Young's modulus of a particular material. So based on that, we'll discuss the problems in next week. So for this week, this class ends today. Thank you for joining, and yeah, okay, I'll end the recording now.